Hello everyone. In the beginning of the class, let us see the new announcements. Okay. First new announcement is April 20th, 2022 class videos uploaded. Hello everyone, I have uploaded the class videos of April 20th, 2022 to YouTube. Their URLs are this, this, and this. Okay, best regards, Wei Zhen. Okay, the second new announcement is the slides of chapter 3 has been updated. Version 20220425. Hello everyone, I have uploaded the latest version of the slides of chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website, multiple input, multiple output techniques for wireless communications. Course content, slides, chapter 3, slides 20220425.pptx. Best regards, Wei Zhen. Okay, the next new announcement is the handout of chapter 3 has been updated. Version 20220425. Hello everyone, I have uploaded the latest version of the handout of chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website, multiple input, multiple output techniques for wireless communications. Course content, handouts, chapter 3, handout 20220425.pdf. Best regards, Wei Zhen. Okay, next let us look at the progress of the last class. Okay, in the last class we have taught to chapter 3 slides, page 33.3 unfinished. Okay, please open the slides of chapter 3 and please turn to the page 33. Okay, this can be proven. Okay, what does this mean? Okay, this means under this constraint, the maximum capacity is obtained when the eigenvalues are all the same value. Okay, so what is this constraint? Okay, for a fixed channel matrix, this equation shows that the sum of the eigenvalues is a constant. So this can be proven using Lagrange multipliers, which are reviewed later in this chapter, but it can also be easily demonstrated empirically. Okay, what is the meaning of empirically? Let us see the handout. Okay, so please open the handout of chapter 3 and search for the word, empirically. Okay, page 33, problem 1. What is empirically? Solution: in a way that is based on what is experienced or seen rather than on theory. Okay, let us go back to the slides. Okay, Next page. Okay, page 33. Figure 3.1. Okay, let us see figure 3.1. Okay, figure 3.1 is a scatter plot showing the capacity for 1000 randomly chose eigenvalue distributions for rho. Okay, where rho is the receive SNR being equal to 10 dB, and R, okay, R is the channel rank, is equal to NT. NT is the number of transmit antennas, is equal to 4. The horizontal line, okay, this line in the plot shows the capacity when all eigenvalues are equal. Okay, so in this figure, Q is equal to 10, where Q is equal to rho is the SNR at the receiver. NT is equal to 4, R is equal to 4. NITER is equal to 1000, where NITER is the number of iterations. So in this figure, the x-axis is the trial index from 0 to 1000, and the y-axis is the capacity from 1.2 to 3 bits per second per hertz. Okay, you can see that there are many gray points in this figure. Okay, totally 1000 points here. And the y-coordinates of these points are all on the line or below the line. Okay, the line means the capacity is approximately 2.8 bits per second per hertz. Okay, so it means that when all eigenvalues are equal, the capacity reaches its maximum. Okay, figure 3.1 is a scatter plot showing the values of the capacity computed using equation 3.11. Okay, let us see equation 3.11. Okay, I have told you that equation 3.11 is a very important equation in chapter 3. Okay. In the later slides, we will usually go back to see this equation on page 22. Okay, this equation is the equation for capacity C, and which is equal to summation I is equal to 1 to R log 2 1 plus rho over NT times lambda I. Okay, do you remember what is lambda I? Okay, let us see. Okay, lambda I, okay, is the are the diagonal elements of the matrix D, and it is also the eigenvalues of the matrix H times H Hermitian. Okay, let us go back to page 34. Okay, using equation 3.11 with 1000 different sets of eigenvalues that sum up to 1. In this figure, NT is equal to R is equal to 4. So each set contains 4 eigenvalues. Okay. The values in each of the 1000 sets of 4 eigenvalues are chosen randomly. Okay, next let us see a special case. N by N 4-rank channel with equal eigenvalues. We now consider an ideal case where the channel is 4-rank. Okay, that is, the rank of the channel matrix is equal to the number of the transmit antennas and is also equal to the number of the receive antennas. the eigenvalues are equal to each other and the MIMO system is n by n. Under this assumption, Nt is equal to Nr, okay, where Nr is the number of received antennas, is equal to N, and R is equal to N. So zeta, okay, what is zeta? Let us review it. Okay, on page 32, zeta is defined as summation I is equal to 1 to R, lambda I. Okay, so zeta is defined as the sum of all non-zero eigenvalues. Okay, let us go back to page 36. So zeta is equal to the sum of all non-zero eigenvalues. Okay, now because the eigenvalues are equal to each other, so we can assume that each non-zero eigenvalue is equal to lambda. Okay, then there are totally r non-zero eigenvalues. Okay, according to the theory of linear algebra. So the sum of all non-zero eigenvalues is equal to r times lambda. Okay, and because r is equal to n, so r times lambda is equal to n times lambda. Okay, then we move the capital N to the left-hand side of this equation. It implies that lambda, okay, here is equal to zeta, okay, here, over capital N, okay, here. Okay, plugging this expression for lambda into equation 3.11. Okay, let us go back to equation 3.11. Okay, we see this equation again. The capacity is equal to summation I is equal to 1 to R log 2 1 plus rho over nt times lambda I. Okay, let us go back to page 37. Okay, so capacity C is equal to summation I is equal to 1 to R log 2 of 1 plus rho over nt times lambda. Okay, and next, because lambda is equal to zeta over n, according to equation 3.15. So lambda can be replaced by zeta over n, and nt is also equal to n. Okay, it is according to previous page, nt is equal to n. So nt can also be replaced by n. Okay, then n times n is equal to n squared. Okay, and this is equal to n times log 2 1 plus rho times zeta over n squared. Okay, why this equation is equal to this equation? Okay, because you can see that it is a term, okay, that it does not depend on I. Okay, so we can treat this term as a constant. So there are r terms of this constant. So so this equation is equal to r times log 2 of 1 plus rho times zeta over n squared. And because r is equal to n, okay, so this equation is equal to n times log 2 1 plus rho times zeta over n squared. Okay, this expression can be simplified by using the fact that for a given channel matrix, okay, a given channel matrix means that this channel matrix is fixed. Okay, the square of the Frobenius norm of H is equal to n squared is equal to zeta. Okay, so first, why does the square of the Frobenius norm of H is equal to n squared? Okay, let us see equation 3.3. Okay, in equation 3.3 for fixed H prime, the square of the Frobenius norm of H prime is equal to nr by nt. And now that nt is equal to nr is equal to n. Okay, so the square of the Frobenius norm of the channel matrix H is equal to n squared. Okay, so then n squared is equal to zeta. Okay, why does n squared is equal to zeta? Okay, let us see the handout. Okay, page 38, problem 1. N squared is equal to zeta. Why? Okay, solution from equation 3.14 of the slides. We know that zeta is equal to the square of the Frobenius norm of H. Okay, let us see equation 3.14. Okay, 3.14. Okay, in equation 3.14, we can see that zeta is equal to the square of the Frobenius norm of H. Okay, let us go to handout. From page 38 of the slides, we know that the square of Frobenius norm of H is equal to n squared. Okay, let us see page 28. Oh, sorry, 38. Okay, so we can see that here the square of the Frobenius norm of H is equal to n squared. Okay, so combine this equation and this equation, we can know that therefore n squared is equal to zeta. Okay, this completes the solution. Okay, next let us go back to the slides. Okay, because n squared is equal to zeta, so in this term zeta and n squared can be cancelled, and the remaining term is rho. Okay, therefore equation 3.16, this equation, that is, this equation becomes C is equal to n times log 2 of 1 plus rho. Okay, this represents the optimum capacity that can be obtained with only CSIR. Okay, where CSIR means channel state information at the receiver. Okay, next let us go to section 3.4, Eigenbeamforming. We now consider the case where both the transmitter and receiver have knowledge of H. That is, both CSIR and CSIT. Okay, where CSIT means channel state information at the transmitter exists, and describe a practical technique that is used to implement spatial multiplexing called eigenbeamforming. Okay, we note that when the transmitter knows the channel matrix H, its optimal strategy is, in general, not to distribute its transmit power equally among its transmit antennas, nor to make the cross correlation between transmitted signals on different antennas zero, which, as we argued previously, are the optimal strategies under the CSIR-only assumption. Okay, we begin by writing the channel matrix in terms of the product of three matrices using singular value decomposition as described in matrix theorem, section 1.9.2r. Okay, please open the slides of chapter 1 and go to section 1.9.2r. Okay, here. Singular value decomposition. Okay, what is the singular value decomposition? Okay, it is introduced as follows. For any complex m by n matrix A of rank R, there are unitary matrices Un by m and Vn by n, and a diagonal matrix Dr by R, which is equal to DIAG sigma 1, sigma 2 to sigma R. Okay, it means that the diagonal elements of Dr by R are sigma 1, sigma 2 to sigma R, such that A is equal to Un by m times this matrix, okay, D0, 0, 0 times Vn by n Hermitian. Okay, in this matrix you can see that there are three zero matrices, and we need to clarify the dimension of these zero matrices. Okay, because this U is n, this is m by m, and the non-zero elements, the diagonal elements in D is sigma 1, sigma 2, and sigma R. So we know that the number of rows of this and this zero matrices is equal to m minus R. Okay, so similarly, the number of columns of these two zero matrices is equal to n minus R. Okay, with sigma 1 is greater than or equal to sigma 2, and sigma 2 is greater than or equal to dots, and is greater than or equal to sigma R, where sigma I are called the singular values of A. Okay, let us go back to slides of chapter 3. Okay, next page. When applied to the channel matrix, that theorem states that if H has rank R, then there are unitary matrices U and V and a diagonal matrix D, okay, which is equal to DIAG of sigma 1, sigma 2 to sigma R. Okay, that is, the diagonal elements of D are equal to sigma 1, sigma 2 to sigma R, such that H is equal to UNR by R times dr by R times V Hermitian R by NT. Okay, where the diagonal elements in D, that is sigma 1 to sigma R, are the singular values of H. Okay, since it is customary to formulate the eigenbeam-forming technique in terms of eigenvalues instead of singular values, okay, because eigenbeam-forming has a okay, it is 25 minutes. Let us take a break.